Okay, guys, let's go ahead and get started. So today we're going to continue with proofs on functions and maybe some on sequences and maybe on some series. I'd like it if today, though, that some of you speak up and kind of walk with me through the proofs, just so I can get a sense of where you guys are at. Right? So let's start with the following claim or proposition. So proposition. Okay, so if f is a function from R to R, so is strictly increasing, then f is injective. Another way of saying one-to-one. Okay, so this is our proposition that we need to prove. Now, when you look at this, I'm not really sure where any of you would start with this one, especially since you were just introduced to the notion of strictly increasing and injective in the previous lecture. I'm not sure how you would go about doing this. Maybe some of you would try a direct proof. Maybe some of you wouldn't even know where to start, right? So what you're going to learn or need to learn in order to successfully be a math major is how to kind of break down the problem ahead of time before you start trying to write down the proof. So let's kind of draw a picture and get a sense of what this is saying is happening. So we have this real value function, right? And it's strictly increasing. Well, what does that look like? It looks something like that, right? This is a strictly increasing function. So injective means what, right? When you're looking at this, you need to be very familiar with the definitions in order to proceed. So it might help to kind of have the definitions written in front of you when trying to figure out where to start. So maybe something like, let me get rid of this graph real fast and write down the definitions over here. So strictly increasing is the same thing as saying if x is less than y, then f of x is less than f of y, right? That's the definition of being strictly increasing. So that's one thing that we need to consider. And then the next is that injective is the same thing as saying if f of x, so if f of x equals f of y, then x is equal to y. Okay. But you should also remember these conditionals, right? You can consider the contrapositive of them as well, right? So this is also the same thing as saying, if we take the contrapositive of this if-then statement, right, we get that if x is not equal to y, then f of x is not equal to f of y. So this is the contrapositive of that, and they both mean the same thing. And they both mean that the function f is injective. So it's useful to know those things, right? When you're trying to tackle a new proof or a new statement that you want to prove, you want to have as much information as you can available to you so that you can work with it and kind of flesh out the details. So then again, we have our picture here of maybe an increasing function. Okay. So, what can we do here? So my first inclination here is to maybe work by way of contradiction. And when I say that, I mean that when you do a proof by contradiction, you get a lot of information. You assume the hypothesis and also the negation of the conclusion. So you have an and there, right? So that kind of gives you the most information to start with. And typically when I encounter a new problem, I immediately go to contradiction first. And then while going through the details of the contradiction proof, if I see that I can do a direct proof, then I'll do the direct proof. So, okay, let's see what happens if we make that type of assumption. If we assume that it's strictly increasing and that it is not injective, right? Let's see what happens. So, let's say, I'm just going to make like bullet points here. This is like my scratch work. So we're going to assume f is strictly increasing. And f is not injective. Okay, so this is by contradiction, right? This is what you assume under contradiction. Okay. So, okay, we're assuming that it is not the case that this happens, right? So if these equal, then those must equal, right? So if we're assuming not the case that that's going to happen, then there must exist x and y. So if we look at this, right, or either one, there must exist x and y where x and y equal, but their images also equal. Right? If we negate this, that's what we would end up getting, right? So then that means that this implies that there exists x and y with, say, yeah, so I'm just going to look at the first one. F of x equals f of y, and x not equal to y. Now you see that would negate that statement. The negation, again, is the hypothesis and not the conclusion. That's what it'll end up being. Right, so that's what we get here. So I'll go ahead and give you a hint now. So the outputs equal, but the inputs don't. And these are real numbers, right? They're real numbers. So the real number line is ordered. There's larger ones and smaller ones, right? If they don't equal, then one of them is bigger than the other, right? So what we can say, and you haven't encountered this yet, but it's called without loss of generality. Um, we can assume x is strictly less than y, right? Because it's either the case that x is less than y or y is less than x. It doesn't matter which one is true, because either one will have that property. So we're just going to assume that x is the smaller one. That's what without loss of generality means. A lot of times you'll see professors do this. Here's another thing. So this right here, this statement, you'll see professors write W, L, O, G without loss of generality. When it doesn't matter which one is smaller, you just pick one to be the smaller one. Okay? So if we assume that, right, since they're not equal, so then x less than y and f of x equals to f of y. So why is that a problem? Somebody speak up. There's a problem that just happened. Anybody? This is a problem. Why? Come on, somebody.
Isn't that statement false?
Well, can f be strictly increasing if this happens?
Oh, no.
No, it can't, right? So that means that, yeah, we get a contradiction, right? If x is less than y, but f of x equals f of y, it's not strictly increasing. But we've assumed it to be strictly increasing. You see that? So this is a point where we have all the information needed to prove it, which we can prove it by contradiction, because we got the contradiction here. Can we also prove this by contrapositive? So can we prove this proposition with a contrapositive proof? Yes or no? Somebody take a guess. Notice, like, we assumed this stuff up here, right? But really, we didn't use any information about being strictly increasing until the very end, where we saw that it couldn't be strictly increasing, right? So if we kind of start like this, right? If we assume that f is not injective, then we use this, right? And then without loss of generality, we can assume that x is less than y. And then we get to this, right? If x is less than y, and f of x is equal to y, this implies that f cannot be strictly increasing. So this looks like a proof by contrapositive, right? We assume the negation of the conclusion, right? And then we get the negation of the hypothesis. So this would be a way of proving it by contrapositive. Like this isn't a proof, but the information here leads to a proof by contrapositive. Before, we could have also proved it with contradiction. And a lot of times you'll see this when writing proofs by contradiction, that it will turn into a proof by contraposition, by contrapositive. Okay. But the goal, honestly, would be to see if we can prove it directly. So the way that some professors look at this, not all professors, but I've had professors in grad school look at proofs this way. The best proof is a direct proof. The second best is contrapositive. And if you have to, the very worst is contradiction. I don't believe this, but some professors tend to enjoy the direct proof the most. So can we prove this directly? Well, let's try. Now that we know that we can prove it, like I know that if I assume that, then I can get that, and then I get that, which means I get that. So I know I can prove it by contrapositive. So now I'm going to try it directly just to see if I can. Okay. So if f is strictly increasing, then that means that, so if x is less than y, then f of x is strictly less than f of y. That's that definition right there. Then we need to somehow use that information to show that it's injective. Well, this is the definition of being injective. If f of x is not equal to f of y, then x is not equal to y. Moreover, this definition is equivalent to the contrapositive of the statement. If x is not equal to y, then f of x is not equal to f of y. So what we can say is, maybe I'll switch up the letters. I can say something like, choose A and B in the real numbers arbitrarily. Okay. And assume this is not, like, I'm not going from there. I'm just saying, assume A is less than B. Okay. So, and assume maybe like this. Choose A and B and R where A is not equal to B. So we're going to see if we can make it satisfy this definition here of being injected. Okay, so A not equal to B, then we can do that without loss of generality thing. So without loss of generality, assume A is less than B. Okay, so then now these two things imply that f of A is not is strictly less than f of B, which is the same thing as saying f of A is not equal, or which implies f of A is not equal to f of B. So if we take two things in the domain, we see that in the range, they don't equal, we know it's don't equal, so then we have that it's injected. It satisfies this definition right here. Okay, so this would be a way of doing it directly, so we can do it directly. Okay, so these are kind of the pieces that we need, and we'll be able to do it. So here, this would be the formal proof now. And we're going to choose to prove it directly because we can. So proof. We're going to say let f be a strictly increasing function. Okay. So then, as we did before in the scratch work, so I'm going to say comma there and choose A and B and R arbitrarily. Okay. So then, since these are, I guess we don't have to say arbitrarily, we can just say choose A and B and R where A is not equal to B. Okay. And so we've made our hypothesis, we've assumed that, and then because of our scratch work, we knew that we were going to need A and B where they didn't equal each other, because we want to eventually show that it has to be the case that this happens. So A and B don't equal each other, so we're right there. So then we can say without loss of generality, we may assume A is strictly less than B. Okay. So then we can use the strictly increasing information now. So we can say, since f is strictly increasing, um, f of A is strictly less than f of B by definition. And then we can just finish it off by saying that this is, so in particular, like that's strictly less than f of B. So we can say something like, that is comma, f of A is not equal to f of B. Just to emphasize that we've gotten to the conclusion that we wanted to, right? So we can just finish it off. So hence, A not equal to B implies f of A not equal to f of B. And then we're done. So this illustrates a whole bunch of things that you're going to start to need. This is a proofs course, so the proofs that we do in this course are going to be harder than the ones that I'm going to do in my discrete math courses, because I need to get you ready for your upper level classes. So let's break down what we did. We read the proposition. I drew a picture to get a sense of what's going on here. Like injective means you're one-to-one. So if I look at a increasing function and I do that vertical line test, or not vertical line test, horizontal line test, I see that it's going to pass at one point. It's increasing. It makes sense to me. I wrote down the definition of strictly increasing just to have it in front of me. I wrote down the definition of injective. And then not only did I write down the definition of injective, as I gave it to you last time, last class, I also wrote down the contrapositive of that definition, because that's the same thing, right? The contrapositive and the original statement will have the same. And we ended up using this in the proof. So after we wrote down that, we did our scratch work, and we looked at, okay, we didn't know where to start at the beginning, so we just started playing around with maybe a proof by contradiction. We convinced ourselves that we could prove it by contradiction, but then also we realized that it was really more of a proof by contrapositive. And once we realized that we could prove it, then we looked at a direct proof and we kind of played around with that and saw that it is possible. But the information that led me to the direct proof started with the proof by contradiction. When I started looking at arbitrary A and B, they just didn't equal each other. And if they don't equal the real numbers, one has to be smaller. So we just picked A to be the smaller one. And then we saw that since it's strictly increasing, the images of those things have to be not equal. So it tells us a lot of information here, right? Because it's strictly increasing, if we have non-equal input, the output, one of them is going to be bigger than the other. So it's necessarily, it has to be injective. That's what it's telling us. Okay. So yeah, I think this would be like a perfect solution to this problem. Okay. So let's look at some more proofs of functions. Okay, so proposition. Okay, so okay, let A and B be sets. So if uh, so if um, f is a function from A to B, S and T are subsets. Say if f is a function from A to B and S and T are subsets of A, then f of S union T is equal to f of S union f of T. Okay. All right, so again, we can't string together any equivalencies here. We're going to have to prove it using an explanation. So let's kind of get a sense of what this looks like by drawing a picture. So maybe here's like set A, here's set B, and F takes things from A and puts them in B. And then we have some subsets S and T of A. Okay, so maybe like this is S, and that's T, right? So, okay, so what's happening here? Let's just say that there's like points A, B, C, D, and E inside of there. So then, if we say look at like this is f of S and this is f of T, right? So then these points get sent in here. That's going to have to overlap a little bit. And then these points get sent over here. Okay. So does this make sense? Well, the union here of S union T is right, like all of this stuff. And the image of that union is the collection of all of the outputs, right? So it would be like all over here, right? So this all of that. Now, if I just look at S, right? So this is S. So the image of S is just here. And then the image of T is just here. So if I union those, I see I get the same picture as I did when I looked at that. So it seems to me that it makes sense. So now I see that I have a set. So this is a set, right? The image of a set is equal to the union of two sets. So the way that you're going to do this is by using an element argument where you show that that's a subset of that, and then that's a subset of that, and then you're done. Okay. So let's kind of work through the scratch work first. So I'm going to start with picking something in there. So I'm going to say let y be an element of this thing. Okay. And my goal, in order to show that this is a subset of that, is to show that we want to show X is an element of that union. That's what we want to show. Okay, so so if X is an element of there, right, and that means that there must exist some X that's in S union T with f of X equal to y, right? Like, if y is in the image of here, right, then there must exist something here that is sent to it. Okay. So then, okay, X is in that union, but we don't know which one, right? We don't know if X is in S or T. Well, that's where we would use that without loss of generality notion. So without loss of generality, assume X is in S, or something like that. So then, if X is in S, right, then the image of X better be an element of the image of S. So that means that f of X is an element of the image of X. I'll write this over as y equals to that, but that must be an element of the image of X. Okay? But if, so y is an element of the image of S, but that means that y must be an element of f of S union f of t. And if it's in that, it better be in that union. So that shows me, so all this together shows me that f of S union T is a subset of f of S union f of T. So I pick something in there, and then it has to be over there, so it's a subset of it. Okay. So now let's do the same thing here. Let's pick something over here and then show that it must be an element over there. So if we show that they're subsets of each other, they must be equal. Actually, now we're going to go the other way. So we're going to show that, so pick X, or no, Y, in this union. Okay. So again, we don't know which one of these sets that Y belongs to, so we use without loss of generality again. So without loss of generality, assume Y is an element of X. Okay. So then, as before, that means there exists an X which is in S, the pre-image of this, with f of x equal to y. Right? If it's in the image of S, then there is a pre-image over here. Call it X. So in particular, if X is in S, then that means that X is in S union T, which means that Y equals to f of x must be an element of f of S union T. Which means that, so what we've just shown, that's a subset of this. So they're subsets of each other, so they must be equal. Okay. So, okay, now we can write the formal proof. We have it mapped out how we should do this. We pick something in there, it must be in there. We pick something in there, it must be in there. They're subsets of each other, and then we're done. Okay, so now let's write the proof. So let y be an element of f of s union t. Okay. I kind of like proofs to be self-contained, which means that I'm assuming that the reader can like look up and read the propositions. So what I'm going to do is I'm going to write the, the hypothesis first. So let f theta b and then s and t. So S be a subset of A and T be a subset of A. And choose Y in the image of the union. Okay. So then, hopefully you remember that what this notation means, right? Just maybe like in your notes real fast, just remember that f of s is equal to the set of all y such that there exists x and s with f of x equals to y. The definition I covered last time. So by definition, there's going to be something in S that is sent to it, or in the union sent to it. The set of all this, such that there exists something in X that is mapped to it. Just remember that, or have it handy when you're looking at this proof. So then by definition, notice I'm starting to write definition all the way out. That's because this is the proofs course, not my other discrete course. And your professor is most likely going to want you to write that out when you're writing the proofs. So write the full thing out. So then by definition, there exists X that's in S union T with y equals to f of x. Okay. So now we know that x is in this union, so without loss of generality, we know it's in one of those. Let's just pick s. So without loss of generality, we may assume x is in s. So then, by definition, y equals to f of x is an element of the image of s. So we've chosen y arbitrarily in this set, and we get that y must be in that set. So we can say that is y, which is equal to f of x, is an element of the union of these images. So that is y is equal to that, which is an element of that. So hence, f of s union t is a subset of f of s union f of t. Okay, so we're almost done. We just need to write. So this is where like having the scratch word next to you is going to be really handy, because this looks long, but really it's just explaining clearly with complete sentences the scratch work that we had before. Okay, so next, let y be an element of the right-hand side. Okay. So again, it's the union. We don't know which one of these sets it belongs to, so we use without loss of generality again. So without loss of generality, we may assume y is an element of f of x. It's got to be in one of them. We don't know which one. Just assume it's in that one. Okay. So then by definition, there exists x that's in S with y equals to f of x. So if x is in S, so we can say something like, in particular, x is in the union of S and T. And then hence maybe y equals to f of x must be in the image of that union. And then we can finish it off by saying this shows that f of s union f of t is a subset of f of s union t. And we're done because they're subsets of each other. And if two sets are subsets of each other, then they must equal. So again, the scratch work is so important to have next to you when you start actually writing these longer proofs. And as the semester goes on, I'm going to start asking more and more detail that I want these full sentences, no abbreviations, in kind of like a flow that you can read. And I'll provide you links with examples of proofs so that you can start mimicking what formal arguments look like, other than just looking at your Zybooks. Okay. So for you at this point right now, the number theory type of proofs, with not like the basic even odd proofs, those should be at a difficulty of about like a 2 or 1.5 out of a 10 scale. And this should be like at like a 6, and the previous proof around a 6 as well. So we're going to start doing these harder proofs, and I'm just trying to kind of ease you into it with showing you how I do it, with drawing a picture, scratch work. Okay, once I'm satisfied with the scratch work, then I start thinking of the formal proof and pay attention to the words I'm using, like hence, without loss of generality, therefore, or this implies, or this shows, right? These are all ways to convey a mathematical argument formally. Okay. Okay, so I think that'll be it for today. I know that I've received many emails from you guys turning in your first exams. If you've emailed me, I've got it. Don't worry if I haven't responded. I have a lot of emails. Just as long as you emailed it to me today, you're good. And I will probably have exam grades posted by this Sunday, hopefully. Okay. Any questions about today? Any comments about these proofs? We spent an hour doing 2 proofs. They take time to write, so it's kind of like a normal thing. No comments? Okay. Well, everyone stay safe. Please get me your exams by the end of the day. And then be vigilant of Blackboard, because I'm going to try to post a lot of supplemental materials for you to read and look at just to get more practice, because proofwriting is nothing but practice. Yeah, I will see y'all next week. Have a good weekend.
Good time. Have a good weekend.